Welcome to the Worldwide Center of Mathematics. Today I'll be going over this week's problem of the week. For the full problem and solution transcript, you can see the link in the description of this video on our YouTube channel. So this week's problem of the week asks you to determine if these two numbers are relatively prime. So an easy way to determine if two numbers are relatively prime is using the Euclidean algorithm to determine what the greatest common divisor of the two numbers is. So I'm just going to go through this problem by going step by step through the Euclidean algorithm, which is something that you would definitely need a calculator for. I mean, unless you really want to do some long division, which I'm guessing you don't, you definitely need to use your calculator for this. So the way that we're going to go about doing the Euclidean algorithm is we're going to put this number over here, the bigger number. Oops. We have 1, 2, 4, 5, 7, 9, 8. And we're going to see how many times what integer we can put here such that we can multiply an integer by this such that we don't go over this. And we're going to add on some remainder. So I'm assuming the viewer is familiar with Euclidean algorithm. So when we divide this out, we end up getting that we can put in 46,987 26 times to this bigger number without going over. So 26 just times this here. So 46987 plus, and then the remainder here is going to be 24136. Okay, so now we're just going to use the same process, shifting this number over here and then this number over into this number's position to keep going down until we get some number such that the remainder, this number over here, is 0. We want it to be 0 such that we can find the greatest common divisor of these two numbers here. And let me just reiterate that by the Euclidean algorithm, if the greatest common divisor of two numbers is 1, so the 1 will end up being the last number here, our GCD is going to be 1, which means the two numbers are relatively prime. So if the GCD of these two numbers is 1, we can tell that they're relatively prime. But we're going to have to go through several steps in order to get there. Okay, so now we're going to take this number here, bring it over here. So we have 46987 equals. So we can only put in 24,136 one time. So 1 times 24136 plus, and then our remainder here is going to be 22,851. Okay, so now we're going to execute the same process again. So 24,136. Again, we have 1 times 22,851 plus our remainder here is going to be 1285. Okay, so the rest of this is just going to be me doing this exact same process over and over again. So I'll just continue writing out my steps so that you can check your work as we go here. So we're going to bring over 22,851. This is going to be equal to 17 times 1285 plus our remainder is then going to be 1,006. Okay, so as you can see, we've already gotten way down here from 46,000, almost 47,000, down to 1,200 and 1,000. So we're getting there. So same process again. We have 1285 is going to be equal to 1 times 1,006 plus we have a remainder of 279. Okay, same process again. 1,006 is going to be equal to 3 times 279 plus 169. Okay, and then we bring the 279 over, so we have 279 is going to be equal to 1 times 169 plus our remainder 110. Okay, so I'm going to go back up here to the top. And as you can see, probably the best way to go about this would be using your calculator, unless you really want a good exercise in patience, number 1, and long division, number 2. So, okay. Going over again, same procedure. We bring 169 is going to be equal to 1 times 110 plus our remainder 59. 110 is going to be equal to 1 times 59 plus 51. And then 59, 1 times 51 plus 8. And as you can see here, this process is really long because we're just doing 1 times 1 times 1 for several steps in a row. So normally the Euclidean algorithm will go much faster than this, but this problem is particularly thorny. So, okay, so now I have 51 going to be equal to 6 times 8 plus 3, 8. Finally, last steps here, 8 is going to be equal to 2 times 3 plus 2. 3 is equal to 1 times 2 plus 1. And last step here we have 2 is going to be equal to 2 times 1, plus finally our remainder of 0. So now we know that because here, by the Euclidean algorithm, this number here in the final step where our remainder is 0 is going to be our GCD. So we've just determined that the GCD, the greatest common divisor, of these original two starting numbers here is going to be 1, which means that the two numbers are indeed relatively prime. So the way that we found that out was by using the Euclidean algorithm, which in this case took a little bit more time than usual, but we still nonetheless got to our answer here, which is much, much faster, regardless of how long it took, much faster than trying factor by factor to see if they have some GCD that's greater than 1, which it would take you a very, very long time to do that. So simplified that process down here, and we ended up getting 1 as our GCD. So for more Problem of the Week videos, you can click our playlist here. To subscribe to us, you can click here. And to visit us at centerofmath.org, you can click this link down here. Thank you for watching.